instead, they have these test points beneath the battery compartment. You'll see these in almost every cell phone. These also exist in the turning point clicker. You can wire these up using just little jumper wires, run them into a GoodFET. Here it is. And then you can reflash it to be anything. Michael Osmond made a spectrum analyzer out of it. Round of applause for him if you don't mind. He couldn't be here, but see every talk he gives. They're very good. You can also dump more obscure stuff. This is a smart water meter from the city of Paris. You can do ant devices. This is a Garmin watch for joggers that will actually track the GPS coordinates of the jogger as well as heart rate from this heart monitor here. And then after the jog, all of this data can be downloaded to a computer through the USB plug. This protocol is open at the higher layers. All of the application layer stuff, all of that is open. You can get it free of any NDA. There's tons of example code. The only thing proprietary here is the link layer. The PHY layer is easy enough to figure out. Like most everything, it's a Nordic RF chip running at 1 megabit per second. The only difficulty is in the MAC address that I mentioned. No one quite knows what the first packets are addressed to, because that's been left out of the documentation. By reverse engineering these devices, we can figure that out, and then because all of the higher layers are identified, it will then be possible to make a completely open ant stack. I think I'll be doing this tomorrow during the advanced badge hacking workshop, just for fun. Also, vulnerabilities run by chip rather than by application. So in the same way that you can find a vulnerability for an operating system within the PC world, you can also identify a chipwise exploit here. For example, every Ember 200 series radio lacks a security fuse. So you can plug right into it and say, please give me a copy of all of your memory and keys, and it will happily oblige you. All of the ChipCon 8051 devices, including the Girltech IMME, protect their RAM from a debugger, but they don't protect flash. So you can connect to a chip and erase it, and then copy RAM out, and have a copy of all of the radio configurations, including keys and channels, encodings, all of that other stuff. You also wind up with problems with bad random number generators. In RSA, which is used for asymmetric cryptography in the IT world, it's not such a big deal if your random number generator is bad, because nonces can be repeated. They can be guessable or known to an attacker. They just cannot be repeated. In elliptic curve MQV, which is the public key cryptography system used by the smart grid, if the nonce is predictable, the private static key can be removed, which is sufficient to impersonate a device in the network. And the sole purpose of this cryptography is to keep devices from being impersonated by others. Some of the third generation Zigbee chips have this right, but every single second generation Zigbee chip screws up the random number generator in one way or another. I'll get back to that in a minute. As for memory exposure, because the access controls exist for protecting code and not data, they're just trying to keep you from copying a product. They don't really care if you can figure out which radio channel it uses. Reprogramming is almost always allowed. Before you're allowed to reprogram the chip, it wants to make sure that it's erased. So an unprivileged user is allowed to erase the entire device and nothing else. But what you can also do is erase and then dump. If you want to get a copy of all of the memory of the Girltech IMME that's in RAM, that is every key, every global variable, all of the radio configuration registers, all of that stuff, you just run these two commands from your GoodFET. You do goodfet.chipcon erase, and then goodfet.chipcon dump data file name from 0 to the end. And you get this nice little image. You can look at it in the I/O region, and sure enough, there is a complete copy of every key in use. There's, you only get the presently tuned frequency, but you can sort of guess at what the center frequencies might be, or at least catch some packets, if not all, should channel hopping be involved. You can do stack buffer overflow exploits, just as you can on a PC. except that there are no stack control mechanisms except for accidental ones. Sometimes RAM isn't executable, but that's okay because your real goal is to get a copy of the software out of the chip when you're doing exploits against these. If you're talking to this badge and you're trying to do a Stack Overflow exploit on it, you would be doing so because you wanted a copy of the badge firmware, not because you were trying to remotely change what the LCDs do. So you can do a return to ROM attack in the same way that you can do a return to libc attack. And Aurélien Francione, a researcher that I've worked with who used to be in Grenoble but is now in Switzerland, he's implemented a complete return-oriented programming attack framework for these chips. So you can actually give it a firmware image and have it search through and find all of the gadgets necessary to move RAM into flash memory to later be executed, even though the chip does not allow the execution of RAM. It's quite a nice attack. You can also do bus usurping. You can connect a good FET to the SPI bus. You can then boot the target device. And then you can halt the microcontroller of the target device just by pulling its reset line to ground. Having done this, the microcontroller on the target stops executing. And it also lets off of the wires so that you, the attacker, now control the radio. And all of the RAM remains intact. All of the registers within the radio remain intact. So you can then just copy the configuration out. In the case of application processors, these are chips which implement a sockets library and expose it over an SPI port. The entire socket library remains open and accessible. So you can then continue sockets which had been opened by the previous device after hijacking all of its sections. In the case of Zigbee protocols and things like that, which are quite complicated, this is very handy because it means that you don't have to understand all of the handshaking and all of the cryptography and all of that stuff. It's already done for you, and you're just left with an open and already running interface. Do these look random to anyone here? This is a snowflake pattern which is generated by a linear feedback shift register. This is one of the worst random numbers generators I've seen. The entire state of this is determined by a 16-bit register that's fed by real random hardware data. That's then shuffled around repeatedly to produce the same sequence of 65,000 samples. So if you plot the first byte that you get along with the second byte that you get in order continuously, you wind up with a snowflake pattern. And given any byte within the x-axis, you know that only a colliding position on the y-axis can be the following byte. Because there are only 65,000 different positions, there are only 65,000 sequences of random numbers that can come from any starting point, which means that there are only 65,000 ephemeral keys that can be used when this device is implementing elliptic curve cryptography. Which means that your lookup table for every key that might possibly be generated is 25 megabytes. Which makes searching trivial. There's also a great paper that came out years ago which says that if you know 4 bits of the ephemeral key, you can recover the rest. Here you know all of them. And you can also recover the private static key. As far as tools go, I use the GoodFET for everything and the Next Hope conference badge for all of the radio work. I use the Total Phase Beagle for SPI sniffing. I've got a couple of boring conclusions here. But if you prefer, I'd like to show you something nifty that I hope some of you can one-up. The badges have a test firmware image, which you can find in the source code, that actually receives packets. So I took this Rosie the robot that my mother made out of stained glass. Cheers for my mother. If I don't break this. Every time its eyes are blinking, it's receiving a packet. See if I can cover this up. Yeah, okay, so no traffic, traffic. Your hands will block the radio signals, by the way, if you try. Like an iPhone. Yeah, just like an iPhone. Ain't nothing like it once was. Yes. So that's about it for this lecture. Are there any questions quickly? I've only got 8 minutes left. Just come up to the microphone and say your piece.
Hello? Oh. I had a brief question about the shorting out these two to make the blue light stay on. Does that interfere with the operation of anything?
You're shorting out which two? The ones on the bottom?
Up here.
Up at the top.
The vertical line that goes up and down.
Oh, that's bad.
That's bad? I'm doing the bad thing then.
Yes. So the vertical column is actually the serial port between the microcontroller and the radio. If you tie those together, the radio will enter an error mode in which all of the lights stay on to tell you that the radio is bad. That's how it goes. If you would like to keep the blue light on, you can tie one of the pins in the horizontal line at the bottom to ground, and that will keep any of the lights of your choice on. So, are there any further questions? Yes.
This is going to be a slightly targeted and rather a following question, but how hard is it to permanently damage the badge, say if you had a bad soldering job or randomly started to wire things together?
If you mis-solder wires together, the chip can't actually supply enough current from the battery to cause damage. And with USB, it's possible but rather difficult to cause damage. If you take your soldering iron and you use it as a chisel, I guarantee that bad things will happen. But you shouldn't worry about permanent electrical damage. This is very well secured against static electricity and voltages in the 3 to 5 range. Any further questions?
How about using two badges as wireless radios to link two laptops together? Could you do that?
Yeah, certainly. There wasn't time to finish the code in advance of this conference, but I was thinking about making a chat room that ran through the badges by USB, where every message that you sent was then relayed by the participants which hadn't seen it to allow for mesh networking between them. And in this manner, you can have laptops throughout the entire badge area communicating. And because all of the packets are sniffed by the badge aggregator network, this could then be fed into a chat log for later monitoring. We're watching you, or at least the OpenBeacon team is.
How much does the CPU and other chips on this board cost? I'm interested because I've done PIC programming, and those CPUs are very, very cheap. How do these compare to those?
The microcontroller in use in this project is rather expensive, on the order of $8 to $10 per chip. Thankfully, we didn't have to pay any of that because Texas Instruments found it within their kind heart to help us. Yes, another round for them. The radio chip, I believe, is just over $2 in bulk, maybe $2.25, and the other components are quite small and cheap. The assembly cost actually accounts for the majority of the cost of production. Yeah. All right. Any further questions?
Yes. Will you be available tomorrow? I know you're going to do a workshop, but you said there are people signed up?
Yes, so the workshop is full. If you come to me with a cool badge hacking project by noon tomorrow, I'll push you in. Otherwise, there physically is no room for more. I apologize for that. But that's the way that it goes. If you've received an email from me telling me that you're in the group, then you are. Otherwise, I don't know. Either bring an impressive badge hacking project or find some blackmail on me. Neither should be terribly difficult, but neither is trivial either. I like beer. If you could bring me IPA, that India Pale Ale. I love America. We should get as much of that as we can.
You briefly showed a French water smart grid application. I'm a little concerned about the smart grid infrastructure here in the U.S. Have you seen wide adoption in this country? If so, what general region of the U.S. is more advanced than others in implementing smart grid?
So there are a lot of test networks. There was a point in time at which it looked as if the smart grid was going to be rolled out overnight, and poorly at that. But now there's significant effort being made into doing a proper rollout. So I'm a lot more optimistic about the success and security of the smart grid than I was a year ago.
Do you know if anyone's gotten this radio working with Atmel or PIC-based processors?
Yes, so the original OpenBeacon badge used a PIC microcontroller, and some of the competing clicker brands use an Atmel microcontroller.